Okay, so this is the second video for the last reading guide for the semester. So in this second video, we're going to look at some more statics problems and one arch dome problem. Okay? All right, so the first problem, we have two supporting structures, and they're holding up a beam with some kind of really heavy object on it. So you can see that these are the supporting structures, and they're holding up the beam with this heavy object like could be anything, a car, a piece of machinery, anything. So the beam, it tells us, weighs 1,500 kilograms. It's 20 meters long, so from end to end, that's how long the beam is. And it looks like we've got a printing press that weighs quite a bit more than the beam, 15,000 kilograms, and it's 5 meters over from this edge. So we kind of know all the dimensions in our problem. What we're supposed to figure out is how much force are those supports, how much force are they using. So I think one of the big keys in this problem is choosing a torque axis wisely. So we're going to look at, since the problem is static, nothing's moving, the sum of the torques is equal to 0 based on static equilibrium. So we're going to start there. And choosing a torque axis will make your life easier or harder. It can work in different situations though. So we're going to pick our torque axis over here on the left to get F sub B. If you pick your torque axis over here on the right, you could probably get F sub A. So you could do it twice that way. I'm just going to use the y coordinates summing to 0 in my second one. But, you know, it's kind of up to you. Okay, so what are the different torques we have if we're thinking about over here? So I'm going to think about the axis is counterclockwise being positive. So that's what I've chosen. You could choose it the other way, but that's what I'm choosing. So in that case, F sub A doesn't have a lever arm, so we don't have to worry about it. F sub B has a 20-meter lever arm, and it's going in the positive direction. So torque is force times perpendicular distance, which is 20 for that one. Okay, then the other guys are going in the opposite direction, so they're going to be negative torques. So we're going to have negative the beam, which we're going to think of just as starting with the center of gravity. So that's going to be its mass. We'll think about all that mass basically being located at the center of gravity. We didn't really do center of gravity, but that's okay. So we'll think about it all being located in the middle, so that's 10 meters away from our green axis spot that we picked. And then we've also got the printing press, which is 15,000 kilograms, holy moly. And it's located, isn't it, 15 meters away from that side?
Mr. Carter, Miss Anglin, and Mr. Walker to the administrative office, please. Miss Anglin, Mr. Carter, and Mr. Walker to the administrative office, please.
Oh, and those are just the masses. To get the torque, I'd better make sure I messed this up when I looked at it the first time. So that's M distance. That's really not force times distance. Like over here we have force times distance. Remember, torque is force times perpendicular distance, so I better do mg distance. Mg distance. Be careful there. That was sneaky. So anyway, we're going to add those over the other side and divide by 20. So I'm just going to, I guess I'll write it out. Jeez. Just for you guys. So 15,000 G is 9.8. I'm just going to write G. And then we've got plus 1,500 G. Oh, this was times 15. Gosh darn it. Times 15 for that one. And this one is times 10 for that one. Okay. All divided by 20. And the force turns out to be, let's see, make sure with my calculator. So 15,000 times 9.8 times 15 plus 1,500 times 9.8 times 10, all divided by 20, and I got 117,600. So I got that many newtons. We don't have that many significant figures. I think we only probably have 2, so it'd be, well, yeah, I think we only really have 2, so I would go 118,000 newtons. But anyway, we could choose now this spot over here and probably get the FB to go away and figure out what FA is using the torques again, using a different axis choice. But instead, I'm just going to look at the vertical forces. These guys all look like they're going up and down. So it looks like we've got FA going up And we've got the other support force going up. We've got the center of gravity, which is that mass G going down, and then we've got the printing press mass also going down with gravity. So don't we know all those things because we just found F sub B, so we're going to say to be static, that has to be equal to 0. So we solve for F sub A, so F sub A, we just said this is going to be plus 118,000. And you subtract this number and this number, and add all that stuff, subtract it, whatever, to the other side, and you get F sub A. I guess I'll go put it up here, right here. So you get F sub A is, it says 44,100. So let's see, does this make sense? Does what we've done make sense based on where the printing press is located? So A is holding up 44,000 of that force, or it's exerting that much force to hold this in equilibrium, and B is exerting, looks like, almost triple the amount of force. Well, that makes sense that B has to exert a lot more force since the printing press is closer to it. So, okay, 2 more problems. Running out of saliva here, so I'm sorry. This problem says you've got like a sign, it's hanging from a cable, so we've got some kind of cable along here, it's holding up a sign. And we've got a hinge here, and there's a beam going out, and they gave us some specifications. So this angle is 30 degrees, the beam is about 2.2 meters long, okay, that makes sense. So how big is the mass? Well, we better get told that. So the mass of this sign, let's say it's 28 kilograms. Three significant figures. Okay, so the question says 2 things. Determine the component of the force the hinge exerts on the beam, so determine the components, I should say, the X and Y components, and then figure out what tension is in this cable that's in this situation. So remember, this is a hinge over here, and the hinge is exerting a certain amount of force on the beam in order for this thing to stay static. Remember, it's not moving. This is a static problem. That's the key. So first, let's just look at the vertical forces. So let's say to be static, the vertical forces have to sum to 0. So we've got the component of F sub h, erase that. We've got the component of F sub h in the y direction. Isn't that going to be like this guy right here? That part of that triangle that we've got. So that guy, and then the tension over here also has just a vertical component, that's F of tension sub y. And then you've got the center of gravity, the beam basically going down, and then you've also got the sign going down over there, don't you? So those are all the y forces going on here. Alright, so we'll come back to that. The x forces, what do we have there? Not quite as many. We have an x force that the hinge is exerting, Fh sub x. And then no x force here, no x force here. Oh yeah, this guy's got like a x force going backwards, doesn't it? So that's why it's minus that part of the tension. Okay, so from this one, looks like we've got that the tension x component is the same thing as the hinge force x component. So that's something good to know. We'll keep that in mind. But it doesn't tell us what either one is, so we're kind of stuck there. Over here, let's see if we can figure out some of this stuff. So F sub hy, we don't know, right? That's what we're trying to find. F sub ty, dang it, I don't think we know that either yet. So maybe we have a system of equations? I don't know. We know these m parts. So let's just arrange those like so. So F sub hy is equal to, we can subtract that one to the other side, negative force of tension, the negative y component of the tension, plus the mass, which we're going to say the mass of this beam is, then we don't have that yet, do we? Let's see. Okay, so I guess I better put it in blue up there. The mass of this beam, this guy, we'll say little m, is 25 kilograms. Okay? So that's going to be 25 times gravity 9.8 minus the mass of the sine, what I call big M, times 9.8. Make sure I get this clear. Okay, and so now we have something relating the y components of the tension and the hinge forces. But that's not enough. So is there some way that we could kind of reason through this problem and get something else? So the book shows a couple different ways. I liked one of them better than the other. So we could do, notice these are all, this is an x here if you notice. So I think we have 4 different variables. So if we've got 4 different variables, I don't think we can do a system of equations. That's not going to work. You might also note that for this tension force, if you just take the tangent and you look at this triangle right here, this triangle, the tangent of that 30-degree angle is one component, the vertical component, over the adjacent, or the x component. So we've also got that going on, but I don't think we've got enough to find any of these things yet, so that's the problem, that's the challenge on this problem. So notice we use the y components, we use the x components. There's not really 3D, we're thinking of this as a plane. There's no shearing force, we're thinking of it going straight in 2 dimensions. So the other thing we didn't use yet was torque, right? So we could say that the sum of the torques is equal to 0 if this is indeed not moving like it's supposed to be. So just like in the last problem, we should probably pick a torque axis. I think we could probably pick either right here or right there. So I'm going to erase some of this. Yeah, we don't need that anymore. Okay, so like last time, we need to pick a torque axis. And we can pick that from either side. So, I don't know. I like their alternate solution. I like the one where they pick the axis through the hinge. So let's just do it over here. Is that what we did on the left last time? We could pick the axis being right here just as easily, but I don't know. I'm just going to be consistent with the last problem. So I'll pick the torque axis over here. So notice the hinge, the FH, is going to basically go away. There's no lever arm for it. But there is a lever arm right here and for those guys as well. So if we take that as our axis, what do we get? So I guess I'll do this in green. So let's see. I guess we got to decide again. Let's go positive is this way, just like last time. So let's see what's going on. So this guy's negative, right? So we've got negative mg. So we've got negative mg. How far away is that? If the whole thing's 2.2, then that's going to be 1.1 for its lever arm. And then we've got, oh, another negative torque here, negative big M G. How far is its lever arm? Okay, it looks like it's 2.2. And then we've got a positive torque right here, don't we? Isn't this guy going to create a positive torque? Just its vertical component, right? Just the vertical component of the tension. So that's going to be plus, positive, the force of tension, that y component. How far is its lever arm? Its lever arm is also 2.2, isn't it? Okay, so notice how many unknowns do we have here? We know this, we know this, we know this, we know this, we just don't know this. It's equal to 0, so we solve for ft sub y. I'm just going to write down the answer. So the tension's vertical component, or y component, is going to turn out to be 397 newtons. Okay, finally we've answered something, but notice I don't think we've answered any. We want the tension, not just the tension's y component. So how can we get the x component? Well, we can go back to what we came up with for the tangent here. So in other words, the x component of that tension is going to be ft sub x. Isn't that going to be, if we rearrange this equation, isn't that going to be ft sub y, like multiply it up to this side, and then divide the tangent? Divided by the tangent of 30 degrees. Remember, make sure you're in degree mode. So it's going to be 397 divided by the tangent of 30 degrees. I am not in degree mode. Ah, now I am. So I got 688 newtons. But that's just the x component of the tension. To answer question B, we want the overall magnitude of the vector, right? So good review here on vectors. So if we want the overall magnitude of the vector, don't we go like this? Or you could just think about your triangle up here, right? You could just use Pythagoras and use your triangle. So you've got that the y component is what, 397? The x component is 688. You can just use Pythagoras, but if you use Pythagoras, or if you think about it as vectors, it's the same thing. So we go 397 squared plus 688 squared, take the square root of that, and you get 793, that makes sense, newtons. That's how much tension is in the wire holding up this sign. Remember, we also wanted to know for the hinge, what were the numbers for the hinge. So I think we have that information basically here already. Didn't we say the hinge's x component is the tension x component? So in other words, that's going to be equal to, what did we find, 688? Okay, so from that part we got that one, check. And then we said the y component of the hinge is going to be equal to negative FTY. Where is negative FTY? FTY is right here, so negative 397 plus 25 times 9.8 minus, should that be plus? FH sub y. So we subtracted tension to the other side, we added this, and we added this. I don't know what happened here, but that should be a plus. So plus 28 times 9.8. So that's going to be the vertical component that hinge is exerting. So let's see what that is. I got 122.4, probably take the 0.4 off and go 122 newtons. Okay, so I think there's all the questions for that one. All right, let's look at one last one. I think this is a little easier. Remember, engineers take a whole class in statics if they're going to be mechanical engineers at least. Or if you go to mines, everybody takes it. So the last one is the dome problem. So we watched part of that NOVA film on domes. I thought this was just a neat little problem. I don't know if you have any like this or not. I don't think so. But it says the dome of the small sports palace in Rome, so this is a real dome, is supported by 36 buttresses, so a whole bunch of buttress support. Remember, domes require a lot of support even though they're domes. So there's 36 buttresses, and each one is a 38-degree angle. They want us to figure out the components of the force FH and FV that each one of those buttresses, each one of these buttress guys, has to, the force that they have to exert to contribute to the dome not moving and falling apart, right? To contribute to the static equilibrium of the dome. So in other words, how much compressive force does each buttress contribute? We're not talking about shear or that other stuff that we skipped from the chapter. So how much force does each one of those contribute? So I think we want to think about the overall load being placed on it first. So if we think about the overall load, that's going to be like the mass of the dome times gravity. So vertically, if you take the mass that's being put on all these buttresses times gravity and just divide that by how many buttresses there are, I think that's going to give you the force that they have to push up to balance out that push down. Yeah? So in other words, the sum of the forces in the y direction is 0, and this dome is not like falling apart. So I think we can put that in there and go the mass of this dome, so a lot of kilograms, stick in our gravity, and divide by 36 to see how much each individual buttress is supporting. So that is 32666.667. So significant figures wise, don't we only have 2? So we're going to go 3.3 times 10. What is that? Times 10 to the 5th newtons. Okay, so that's how much vertical compressive force each buttress has to do to keep it in equilibrium. How about the horizontal force that each buttress has to do? So I think for that, if you just like turn this around and think about it like this, so this is like FH, and this is like your FV. It's just a triangle, so do a good old tangent. Tangent of 38 degrees is opposite, adjacent. So in other words, the horizontal portion of that force that each buttress has to do is the vertical portion divided by the tangent of 38. Same trick as the last problem, right? You multiply that up to the other side and divide your tangent. So it's going to be that number divided by tangent 38. So it looks like I got 418, 114.267, or about, with significant figures, 4.2 times 10 to the 5th, about 400,000 newtons of horizontal force that those buttresses have to exert each. Out of all the 36, they all have to do that much each. Okay, hope you found this interesting.